Hello, welcome to a little talk about interparticle forces. My name is Chad Houston. It's also called bonding. This is kind of bonding part two. If you're watching this, what I would like you to do as a student of mine is to download the guided notes below and make sure to fill those out as we go. Also, there are links within those notes. It's assumed that you know something about covalent bonding, ionic bonding, metallic bonding. If not, the good news is that all of these links deal with great little short videos that cover those topics. And if you want to know where those videos are and a lot more in chemistry, check out my YouTube station right here. Okay, so bonding is basically the definition of bonding is essentially any electrostatic force between two objects, which means that one definition covers a huge amount of stuff, which is why we can't just cover it in one video. But really what that talks about is that every atom has neutrons, protons, and electrons. The protons in the nucleus give the positive charge. The electrons provide a negative charge. Remember, like charges repel, positive charges attract. So that positive nucleus can not only attract other electrons, but the electrons in the atom, but electrons well beyond the atom, which is why it will attract to other elements. However, as those electrons are drawn in, like charges repel, and they also start to push away. So we have this complementary tension. So to demonstrate this in a nice little model, we have this atom smith right here. And if you take a look, here is a model of a hydrogen atom with a nucleus and an electron in the electron cloud, which is the probability for we can find it. Here's the other one, and they're far apart. This nucleus attractive force goes way out here, but it's too far away to grab this electron. But watch what happens here as I bring it in closer and closer and closer, so you can see it. So I'm gonna bring it in closer here. They get close, too close right there. So what happens is, as we get closer and closer and closer, the nucleus of one grabs the electron of the other, and they start to share and pair up. Finally, and this part here, this part we see here, this is just a model, but it's showing this is sort of like the bond. In real life, you don't see these lines, but they're just trying to show that. Now, watch what happens down here as we go. It's basically the most energetically stable it is, which means this nucleus is pulling on both electrons, but if it pulls any more, the electrons start to repel and go up in energy. So that's kind of the sweet spot. That's where everybody has their happy balance of attractive and repulsive forces. And that's what causes bonding and stickiness and interparticle forces. This is just a small example. And that idea about positive and negatives attracting is called this Coulombic interaction. Now, the way this works is you typically, in an element, you have a nucleus with a bunch of positive charges, and they're constantly attracted to negative charges, pulling in those negative charges, which is the blue. And what affects it? Well, if I have more positive charges, this attractive force gets greater. And if they're closer, the attractive force increases as well. The opposite's true. If I have less of these or the electrons are farther away, then the forces are much less. And on the other hand, you have these electrons that are being repelled by other electrons, which keeps them away from the nucleus. And so this is basically a balance. To see, to go back and forth. And this positive can actually extend beyond this to grab other electrons, or these electrons sometimes can leave, and that's where we get reactivity. That's basically Coulombic interaction in a nutshell, but we're just trying to hit the point that these forces play a huge role. Now, you might think, man, that's really confusing. Well, it can be kind of a crazy, balancing game. It's much easier with the chart of electronegativities done by a genius of a scientist called Linus Pauling. And essentially, he made everything much easier for you. Here's what you need to know. In this periodic table, any number where there's a high number, scales 0 to 4, and there's no labels on it, except it's the electronegativity scale, the higher the number means that in a covalent bond, the elements with the larger electronegativities want to pull on the electrons in the bond covalent bond, the pair of electrons, more. They spend more time on that atom, whereas smaller numbers, they don't pull as hard. Those elements won't pull as hard. Okay, why should we care about this? Well, let's use an example. Imagine that we have fluorine and fluorine, F2. It's a molecule, and we have F2 here. If they are sharing equally, if everything's shared equally, they both have a high number, but they both share, they cancel each other out. You can imagine that there's a very equal distribution of electrons. There's no side that's somewhat positive or somewhat negative. The interparticle forces, that means between F2 and F2, it's called London dispersion forces. Is that going to be a very strong force? No. That's because, again, that it has nothing to grab onto. That's why these London dispersion forces, all things being the same, they're very weak forces. That's why this is a gas at room temperature. How do we increase these London dispersion forces? You just make the molecule bigger. But again, as long as there's equal sharing, there's no side that's kind of negative or kind of positive, we're not going to see many interparticle forces there. So we could predict it might be a gas at room temperature, all things being the same. Now, let's imagine we do something called dipole-dipole. Think of having the poles of a magnet, right? So here's an example, and I kind of have one here, and what I'm going to show you here is, let me just a little bit bigger. Here is, for instance, a model over here of carbon attached to 3 hydrogens and a chlorine, which I kind of have here, and I wasn't able to get the right colors, but I think you kind of see the idea. And what we're trying to show here is that the chlorine is very electronegative. It's pulling on those electrons a lot more. Even though we're sharing covalent bonds, the electrons, there's more of a density of electrons on this side, a lot fewer on this side. This is somewhat positive, somewhat negative. So that being the case, what would happen if another one of these comes in? Well, if this side is kind of negative and this side's kind of positive, same for this, opposites attract, it's going to want to start to combine like this, and they stick together more. So these might form a liquid at room temperature. What if we have this permanent dipole in a molecule, but we have something called hydrogen bonding? Now, hydrogen bonding is really important for a reason here. So again, this is in this realm of intermolecular forces, covalent bonds, but now we've got something else. For hydrogen bonding, any compound that has HF, HO, or HN in it. So think of like water, NH if you're taking biology, DNA, HF, hydrofluoric acid. That's one thing, we'll get to that later. But when you see these, it means hydrogen bonding is probably going to occur. What does that mean? Okay, so this is a model, and let me explain to you. Here is a model of H2O. And here, over here, on this side, this is more electronegative. This is less. This pulling more electrons. The red up here means it's kind of negative. Down here, it's kind of positive. If that's the case, another one comes in. Again, opposites attract. The somewhat negative side up here is going to go to the somewhat positive side down here, and they start to attract. So when we talk about hydrogen bonding, it's really, really important to understand. We're not talking about the bond between the oxygen and the hydrogen here. It's not it's between the molecules, intermolecular. Hydrogen bonding is between this hydrogen here and the attractive force to this O right there. And you just look for HO, HF, or HN. This is what controls the weather on our planet. Okay, this is why we're alive. This is really, really, this is what keeps us alive. This is a big deal. I hope you found this helpful. Thanks a lot. And if you have any questions, don't be afraid to ask.